Alright, so the second half of the video got cut off, but I will go through this one just a little quickly. So here we use the x equation because I had the x velocity and the x distance to use that to find my time, and then I asked the height above the ground that it hits the wall. So this is not the maximum height that happens right here, this is the height right here. So I have to use this time that we just calculated because that is the time until we hit the wall. So I can use the delta y equals v naught t plus 1/2 et squared because I still know my initial velocity in my y direction. I now know my time and I know acceleration, so that will give me a height of 3 meters. And the reason we're not using v equals 0 at the top is because I'm not asking at the top. I'm asking for this one right here, and I don't know, like, it's not like any specific like half of the height and anything like that. So I have to just use this x distance because that has been given to me. Number 3, we have a v naught at an angle theta, and I want to know how high it goes, so I'm looking for delta y, and I didn't put this, but I meant to put use g for your acceleration due to gravity. As soon as you have an initial velocity and an angle, the first thing you need to do is break it up. Your x velocity is v naught cosine, and your y velocity is v naught sine. And then I am looking for the height, the delta y, and because this is talking about like the very high point that it goes to at the very top, I can use that the y velocity goes to 0. Now a lot of people will look at this and be like, oh, find t and then plug in, but you actually don't have to because I have v naught a, v, and I'm looking for delta y. So that's just this third equation, v equals v naught squared plus 2a delta y. This is 0. This is the y component of the initial velocity, which is v naught sine theta, and don't forget the squared. A is your acceleration due to gravity, and then delta y is the height that I'm looking for, so I'm trying to solve for this right there. This I can just subtract over. It gives me negative v naught squared equals 2g delta y, and then I can divide over to cross off the 2g, and that gives me my answer. Number 4, we have a student mass m that runs horizontally off of the cliff of height h, and it lands in the water some distance d away. So this is a horizontal projectile. I have some initial velocity, I don't know it, v, that's in the x direction. I know the height, that is the displacement in the y direction, and I know d, that is the displacement in the x direction. Because this is going and running horizontally, that means my initial velocity in the y component is nothing, right? It's only going horizontally, so v naught would be 0 for the y. I plug in displacement x, displacement y that we're given, and then acceleration is g because it says use appropriate physical constants, so we'll just use g for acceleration of gravity. And I asked you to determine the time. Now there's not enough information for x, so I'm going to use a y equation. I'm looking at delta y, a, v naught, and t. That's the second equation. Now it's just plugging in. Delta y we said was h. V naught in the y direction is 0, so that goes away. 1/2 a is gt squared. Multiply the g up, multiply the 2 up, divide the g up over, and then that's t squared, so the last step is to square root. Now part B is asking us to determine the velocity they need to run off the cliff with, so that's the x velocity I'm looking for, which is good because my x equation is v is delta x over t. I know delta x, it's this distance d, and then I also know time, that's the point in part A, was to get an expression for time. I could not just leave it as d over t because it says you want your answer in terms of hd and appropriate physical constants. I can't put t in there, right? That's not something that's been given. I can't have that in my answer, but I've already solved for t, so you're just plugging it in for t the same way you plug in d for delta x. So I can just think of it like that. Number 5, so we have a ball drop from the top of a building of height h. It falls from rest and accelerates until it hits the ground below. How much time does it take to fall the first half compared to the time it takes to fall the second half? So if I drop it for some height h, obviously it's going to fall down, it's going to pass the halfway point and then hit the ground. I'm asking how the time it takes to go from the height to the halfway point compares to the time it takes to go from the halfway point to the ground, and it's not the same. So the answer is actually that the time it takes in the first half from h to h over 2 is longer or more than the time it takes to fall down. Because if you think about it, this is something falling down to the earth. It's accelerating the entire time. So down here, it's going faster than it is right here. So even though they might be going for the same distance, if this one is going faster, then it takes less time. This one going slower means it takes more time. So the answer was the time it takes to fall the first half is longer than the time it takes to fall the second half. And you definitely want to say like because it's traveling faster, but you also need to tell me why it's traveling faster. So because it is traveling faster on average this second half, and the reason why it's traveling faster is because it's had more time to accelerate. And it's accelerating with negative 9.8. So in this half, it's going faster right here than it was at the top, and it's still accelerating. Whereas the second one, at h, at the top, we have v naught is 0 at the beginning of this half, so it's slower on average. Number 6, so we have an object that is pushed up and then it slides up and falls down. We wanted to describe the motion, so I decided that I want this direction, this up and over, to be the positive direction. So it starts with some positive velocity, and then because it's going up and it's not going to keep going up, that means there's some acceleration against it. So that acceleration would be in the negative direction. So your description is just, it starts moving up, and on its way up it slows down until the velocity is 0, and then it turns around, and in this case, on the way down, it should be accelerating. So it starts moving up the ramp, slowing down until it stops for an instant at the top, and then it comes back down, speeding up on its way down. Drawing the position, velocity, and acceleration graphs. So I like to start with velocity and acceleration. I think they're a little bit easier. Acceleration, so I know that the sign of my acceleration is negative, and I know that my acceleration is constant the entire time because on its way up, it was being pulled back down, and then on its way down, it was being pulled even faster. So there was no point where the force pulling it down was just turned off. So my acceleration graph was just constant and negative. My velocity, I started with some positive velocity. It went to 0 at the top, and then on the way down, it was negative. It was slowing down on the way up and speeding up on the way down. So I start positive, hit 0, and negative, and this shows it slowing on the way up and then getting faster on the way down. And then lastly, the position. So I want it to be going in the positive direction, but getting slower, so that would be getting flatter like this. And then it's on the way back, I have a negative velocity, it's going in the negative direction, and it's getting faster, so it should be getting steeper, which is where I get this position graph. And then another type of motion that would produce that, something thrown up in the air, would start with some positive velocity, and it would have a negative acceleration, specifically negative 9.8, that would slow it down and cause it to fall back down faster, so it would look something like this. And the last one, I've got a velocity versus time graph for two runners, A and B. So I first just quickly described. So B, I have a constant velocity of 6 meters per second for runner B. And runner A started with 0 velocity, but is getting faster. So he started from rest and is accelerating. So this just helps to get your brain in order. A is asking which one is in the lead at 6 seconds. So I looked at 6 seconds. And it's asking us to answer this qualitatively. So I don't want to have any numbers, no equations. It's got to be like words. It's got to be conceptually who is in the lead and why. So conceptually you can think about, well, runner B has been going at a constant velocity the entire time. So he's been going faster from the beginning. He was going faster. Runner A started off slower, right? They started from rest and is accelerating, but has only now, at this point, only now reached the same speed. So I said runner B would have the lead because he's been going faster the whole time because he was going at a constant speed. B was going slower on average because he started from rest and only just got up to the same velocity as B. Sorry, my handwriting is terrible. And then B is asking us to answer the same question, but now I want to answer it using equations. So not saying like, oh, well, because he's going faster, he'll go farther. Now I want you to actually plug in numbers, show equations. So So B is easy because B is going at a constant velocity. I can use V equals delta x over t, my constant velocity equation. It had a velocity of 6 for 6 seconds, so then you just multiply up and you get the displacement for B was 36 meters. Now for runner A, it is not at a constant velocity. He started with velocity 0, so that means V naught would be 0. It's still 6 seconds, that's still t, but I need to know my acceleration. So I look, he went from 0 to 6 meters per second in 6 seconds. That means an acceleration of 1. So V naught 0, time is 6, acceleration